Some of the kids at the end of class asked for a quick review and maybe some guidance for the homework on the back side of the sheet we started during class today. If you take a look up here at the diagram up top, you can see that we've got a cart, a string, and a hanger. We decided to define the system as just the cart. We assumed that the track was frictionless, that the smart pulley was massless, the string was massless, and we started off with some mass on the hanger down here. And we drew a force diagram. So after some discussion, we all agreed that there would have to be a force of gravity on the cart by the earth, and an upward force that's the same size, force normal on the cart by the track. And the other piece of the puzzle that we discovered as time went on, there couldn't be any friction opposing the motion because we said it was frictionless, but there would be a force of tension to the right, force of tension on the cart either by the string or the hanger, depending on how you want to look at that. And that last force we draw there represents the net force, or if you add up all the forces, that's what would be left over. So we took a look at that and tried to see what kind of motion did we see. And it was pretty obvious from what you guys saw that we had a velocity versus time graph that had this overall shape, and that the slope of that graph was the rate of acceleration, so we had some uniform acceleration. At that point, we talked about how could we manipulate this system. So we decided to keep the mass of the system the same, and we looked to see what would happen if we increase the mass of the hanger and therefore increased the net force, and while maintaining the mass of the system. So we went ahead and ran some trials where we added more and more mass to the hanger, and we again took accelerations from the shape of the velocity, from the slope of the velocity versus time graph. We were able to find some average forces applied, and from that we were able to build an acceleration versus net force graph. And the slope of that had something to do with the mass of the system. It actually had to be 1 over the mass of the system. But we said from that equation, in general, we'd say, while maintaining the mass of the system, because we didn't change the mass of the cart, if we increase the net force, so if we pulled harder on the same mass, the acceleration would increase. Right? And that showed up here. If the net force was this amount, it would give us that acceleration, and if we doubled the net force to here, it would actually double the acceleration. So we could say, in general terms, that the acceleration and net force were directly proportional, or we came up with the equation that the acceleration was equal to the net force divided by the mass of the system. So we then took a second look at the experiment, and we said, well, what if we, instead of keeping the net force, instead of keeping the mass of the system the same, what if we kept the net force the same? So we didn't change the mass of the system. We put a certain amount of mass on the cart, on the hanger, and left it there, and we kept adding masses to the cart. We kept adding black bars to the top. And in general, if we maintain the net force, so that was kept constant, if we increase the mass of the system, what happened to the acceleration? And you saw that it sped up less quickly, so the acceleration decreased. I don't recall if we showed this next graph on here or not, but basically it said as the mass got bigger and bigger and bigger, the acceleration got smaller and smaller, so the shape of the graph would have been like this. But with some analysis of this graph, it would turn out giving us this exact same general equation. Acceleration is equal to the net force divided by the mass of the system, which we said was Newton's second law. So how can we use that to solve problems? For the homework for today, it says if you kept the mass of the system the same but decreased the net force, well, that's the opposite of what we did over here, right? We said as the net force got bigger, the acceleration got bigger. So if the net force got smaller, the acceleration would get smaller. So if you decrease the net force, the acceleration will decrease as well. If we had said, if we increase the net force, the acceleration would increase. We did this problem in class. Sorry, I should have filled this out already. We said if you have an acceleration, They want us to find the acceleration if you have a 0.5 kilogram mass experiencing a net force of 8 newtons. And again, you guys did this one in class, so this one's probably already done on your paper. So we said the net force was 8 newtons, and you divide that by the mass of the system, which is 0.5 kilograms. And if you punch that into the calculator, 8 divided by 0.5 is 16. And when we talked about newtons per kilogram, we could do some fancy mathematical analysis, but if we're looking for acceleration, the units turn out to be meters per second squared. Next up, if the mass of the system increased while the net force stays the same, what happens to the acceleration? Well, if we go back and look at that second version of the experiment we did today, as the mass got bigger and bigger, right, the acceleration got smaller and smaller. So we'd say as the mass of the system increases, the acceleration would decrease, and that's assuming that the net force doesn't change. Next up, it says find the net force of a 10 kilogram mass that is accelerating at 3 meters per second squared. We have the mass of 10 kilograms, we've got an acceleration of 3 meters per second squared, and they want us to find the net force. So we can start with the same general equation. Acceleration is net force divided by the mass of the system, and we can plug in the things we know. We know the acceleration is 3 meters per second squared. We know that the mass is 10 kilograms, and we need to find the net force. To find the net force, we have to have that on the side by itself. So to get rid of the 10 kilograms, we have to multiply both sides by 10 kilograms. And so we've got 3 meters per second times 10 kilograms, and 3 times 10 happens to equal 30. And a kilogram times meter per second squared turns out to be a newton, which is our measurement of net force. And I know that you guys know that acceleration is measured in meters per second squared. We know that mass is measured in kilograms, and we know that newtons is a measurement of force. I won't ask you to show the unit analysis of how that works out, but you do need to know which units go with which variables. Next up, it says find the mass of a hover puck that's experiencing a net force of 8 newtons accelerating at 2 meters per second squared. So we can start with the same general equation with Newton's second law that says acceleration and net force are directly proportional, while acceleration and mass of the system are inversely proportional. We can plug in the values that we know. We already knew that the net force was 8 newtons. We were told the acceleration was 2 meters per second squared, and they want us to find the mass. So the acceleration was 2 meters per second squared. We know that the net force was 8 newtons, and we have to find mass. Now, to find the mass of that, mass is on the bottom of that fraction. So to really solve for mass, it's going to be best if we move that up over there. To do that, if we multiply both sides by mass of the system, now we would have 2 meters per second squared times the mass on the left side, and that equals to, I lost the tip of the marker, which is equal to the 8 newtons. Now, to find mass, we have to get rid of the 2 meters per second squared, so we divide both sides by 2 meters per second squared, in which case these cancel out over here. Now we just have mass is equal to 8 divided by 2 is 4, and a newton divided by meters per second squared. Well, we're trying to find mass, so we're going to actually measure in kilograms. And I won't ask you to show the unit analysis for that on the quiz. So we got that. Number 6 says, if you double the net force and the mass on a system, what will happen to the acceleration? Well, to do this, I thought maybe we could just take a look at the one from problem number 2 that we did up here earlier. We already know that if you have 8 newtons of net force applied to a 0.5 kilogram mass, that the acceleration is 16 meters per second squared. So I thought maybe we can just use those values and double the net force. So the problem we had up there was acceleration equals net force divided by the mass. The net force is 8 newtons and the mass is 0.5 kilograms. And they want us to double both of them, it looks like. So let's double both of those. 8 newtons would become 16 newtons of net force, and a half a kilogram doubled would be 1 kilogram. And we know that 16 divided by 1 is 16, and a Newton per kilogram gives us the units for acceleration. We happen to do meters per second squared, and boom. So it looks like if you double the mass of the net force and the mass, if you double both of them, you get the same rate of acceleration, because it's the same answer we got for number 2. And lastly, it says a 12 kilogram bowling ball, so that is the mass of the bowling ball, moves at a constant velocity of 6 meters per second. What's the net force? Well, this to me sounds like a tricky question. If it's moving at a constant velocity, what's the acceleration? You're right. If it's moving at a constant velocity, the acceleration is 0. And what do we learn about objects in motion? Objects in motion will remain in that motion unless a net force acts upon it. So if it's moving at a constant velocity, that would mean that the net force must equal 0. The forces have to be balanced for something to move at a constant velocity, so this is a little bit of a trick question. We found out there's 2 situations when the net force is 0. One when the object moves at a constant velocity, and the other would be when the object is at rest. If there is a net force, it must be accelerating, and it would be accelerating in the same direction as the net force. I hope that helps.